Hello, we are Group 6, and today we are presenting our project on predicting heating and cooling loads for residential buildings. HVAC systems account for nearly 25 to 50% of a building's total energy use. Because of this, understanding what drives these energy demands is essential. Our task was to examine how different architectural factors influence the heating and cooling needs of a building. Accurately predicting these loads is important for improving energy efficiency, reducing costs, and supporting environmental sustainability. Instead of relying on manual estimates, we chose a data-driven approach that uses machine learning to model and predict energy needs based on building features. Before building our model, we reviewed several research studies to understand how energy load prediction is approached in the real world. The literature consistently highlights that modern buildings are becoming more data-dependent, and accurate prediction models are key to optimizing HVAC systems. One study emphasized how sensors and machine learning algorithms can improve building energy monitoring. Another article focused on the role of load prediction in integrating renewable energy and designing energy-efficient buildings. A third study examined intelligent optimization methods that help estimate a building's thermal performance more accurately. Together, these papers showed that architectural features such as wall area, glazing area, and building orientation play a major role in determining heating and cooling demands. They also help validate our choice to use machine learning since the research supports its effectiveness for predicting building energy loads. With this background, our project applies these ideas to create a model that predicts heating and cooling loads based on key building characteristics, helping us better understand which features have the greatest impact on energy performance.
The problem at hand requires us to collect a dataset that contains several features of buildings like wall area, roof area, glazing area, and orientation, among many others, and their associated heating and cooling loads. We first started by importing the necessary libraries that we will need to use, such as NumPy and Pandas. We then started by creating a table and creating a summary using the .head function. We also used labels to make the table easier to understand on each column, describing which attribute correlates to each number. We also used the .describe to give us more information about each attribute, and .shape to give a summary of the amount of cells in our table. We also used .info to get a general information about the table, and .null and .sum to get rid of any unnecessary information. The first step in our project was exploring relationships between features and energy loads. We used Python to calculate correlations between all features using the .core function in our code. We then used histograms to give a visual representation, creating a different graph for each attribute. We then used Seaborn to create a plot paragraph. This part is similar to a histogram, but these plots, we can see the relation between the values in each column. However, because that is more difficult to understand and to see, we used a heat map, which allows us to easily spot strong positive and negative correlations. We next used more libraries to create training data and train our model to create better predictions. Next, we assessed the quality of our model. We did this by using .predict, which helps with creating more accurate predictions. Finally, we had to input the database and interface. Here's where we created our functions. This function is designed to take a set of architectural features as its inputs and use the previously trained linear regression model in determining the results of given features combinations below our 3 cells where we predicted the heating and cooling load for the given 3 different features as required by the assignment.
After the training of our models, we tested different feature combinations in order to find out which one gives the best predictions. Indeed, some feature combinations are consistently better than others, a finding that provides a key insight for energy modeling as well as architectural design. Another interesting observation is that small changes in the building features will bring large differences, such as an increased window-to-wall ratio or a changed roof area, which can greatly affect the heating or cooling load. This justifies that design decisions should be made more carefully in early stages of planning. In summary, our project demonstrates how machine learning can help energy-efficient building design by providing an accurate prediction of heating and cooling loads. Combining data analysis with feature selection and predictive modeling provides the architect and engineer with a practical tool to reduce energy consumption while sustaining comfort.